Hi, my name is Serenity Kosorok, and I'm going to be giving a presentation on Zophobas atratus, or Zophobas morio, which is also known as a superworm. Their habitat is naturally in the tropics, but they're bred worldwide for many uses. They're holometabolists, so they experience all four phases of metamorphosis. They look small, but they're actually really big for their species. They normally eat decaying plant and animal matter, and they're preyed upon by rodents and coyotes. Because they're bred, they are common and not endangered. Here we can see their four phases again, some defense mechanisms, and some uses that humans have for them. They fit into the categories Animalia, Arthropoda, Insecta, Coleoptera, Tenebrionide, Zophobas, and my species here. I'll hit on these specifically later, but right here I wanted to highlight that to be part of Insecta, they have three tagmata, and this specifically includes the head, the thorax, and abdomen. Then, to be part of Tenebrionide, those legs, the front legs have 5 segments, the middle have 5, and the back have 4. In the arthropod group, they exhibit a hard exoskeleton that contains jointed appendages. Arthropods are from the Cambrian explosion about 550 million years ago, and they are said to evolve from a walking cactus fossil. This sparked a debate in the scientific community that was a big deal because it had previously been thought that these arthropods had their bodies become hard before the legs evolved to become hard. But this fossil was found with legs that were hard and a body that was still soft. So this shook that hypothesis that previously had existed, and this debate is actually still going on today. Here we have two diagrams side by side. This is a general insect diagram. It is a grasshopper example, but it's been labeled with some general labels that insects have. You can see the head, thorax, abdomen. They both have evolved to have wings so they can fly and get away from predators, and legs so they can get away from predators and maybe get to food better, and eyes for similar reasons. But something really specific to the evolutionary phenotype of the beetle is the fact that it has this elytron. We can also maybe call that a genotype too, but this protects its soft inner body and also the wing. One of the most exciting things about Coleoptera is that it is one of the most diverse orders, and we have tons of fossils. I just pulled 4 here that we can see, but there's actually hundreds. That a lot of them are preserved in amber, some in stone. One thing that's really exciting is that we can actually see multiple life stages for these species. So we have a rare wireworm, which is a click beetle larvae right here, and then we also have our beetle. This is a Tenebrionide hypothesized family tree. They are so diverse, so there's a lot of incomplete records. It's generally thought that these evolved from transitional species Alphotopsis initialis, as a well-preserved fossil of this species is known to contain the major characteristics of Tenebrionide. Intersegmental abdominal membranes, which means that those 3 parts I mentioned earlier have membranes connecting them. Defensive glands, open mesococcal cavities, and trochantin, and that's just their legs. When it comes to the speed of diversification, following an extinction event closing the Permian period about 286 million years ago, there was this explosion of tons of evolutionary differences that they refer to as radiation. So it was just tons of different species coming out all at the same time. So that is part of one of the things that they attribute to why these are so diverse. We can see that the diversity sometimes is really small. These beetles from a distance might look the same, but they're actually different. Something that superworms get confused with a lot is mealworms, but they're actually completely different. We can see that the ends of them are not brown on the mealworms here. This right here is just a superworm that is molted. Some special features include the fact that these Zophobas can actually break down, they have enzymes in their gut that can break down plastic. They also secrete defense mucus to defend themselves, and when they're all together, sorry, my videos are having a lot of trouble loading right now, but when they're all together, they actually will delay pupating until they're isolated. When it comes to convergence or similarities on some of those specific things, there is a moth that preys on beeswax, And we can see that it will delay pupating until it has been isolated as well. This can help with a lot of things with space and food that's available. Mealworms will try to eat plastic, but their stomachs actually don't have the enzymes that they need to break down the plastic, so they are more likely to die if they do that. Within the same Tenebrionidae family, we can see that the bombardier beetle, right here, he actually secretes also a defense mechanism that can make predators go away. Sorry, I'm just clicking through my videos because they're having so much trouble. When it comes to analogy, there is actually fungi and bacteria that can break down plastic using hydrolase. Zophobas morio actually uses a myriad of gut bacteria rather than producing a specific enzyme to do the same thing. Here's some geography maps showing that they really do occur all over the world, and here are my sources. I love Zophobas morios. I think they're really cool, and I'm really excited to see the research that comes out regarding how they can break down plastic and how we can apply that to our landfills today. Thank you.